All right, so we're going to look at an example problem in time dilation, and it reads, an aircraft flies 5,900 kilometers per day around the Earth at 210 meters per second. The aircraft returns to its starting point 4 days later at the same speed. How much has the pilot aged compared to their airbase colleagues? All right, so this is going to be a problem relating these speeds and one reference frame and another reference frame and this idea of time dilation. Excuse me. So we know that the time that the person on Earth, the observer on Earth, is aging, the time of the person on Earth is aging, is going to be related to, well, that airplane flies 5,900 kilometers in 4 days. So how long the distance divided by how fast that plane is going is how long it's going to take that plane to go around the Earth 4 times, or whatever that flight pattern is. So how much distance is that? Well, we have 5,900 kilometers. We know there are 1,000 kilometers. No, there are not. There are 1,000 meters in 1 kilometer. And we know that they do that 5,900 kilometers each day, and they go for 4 days. So the total distance D is going to be equal to 236,000. So 2,360,000 meters. Now, the time it takes for that observer to be watching it go, that traveling that full time, is this 2,360,000 divided by how fast that plane is going, which is 210 meters per second. Now we're not going to calculate that out. We're not going to give a number because we're dealing with really small numbers, so we don't want to have any rounding errors happening. Okay. All right, so this is the change in time of the person on Earth. We know that the person in the airplane that's moving around, their event is going to be smaller, right? So we know that based on our time dilation understanding that their event is going to be the proper time. So that's going to be our delta T naught. And we know that delta T, based on our time dilation relationship, is delta T naught over the square root of 1 minus the speed squared of the object, the plane, divided by the speed of light squared. Okay, so the event of that person going around the circle in the plane 4 times, that event for them is our proper time. Okay, so we then can use this relationship, and we have delta T times the square root of 1 minus v squared over c squared is equal to our delta T naught, so our proper time. When we have all the information we need to solve for that proper time. Now that's how long, that's the time of the person in the plane, okay? And this delta T is the time that the person on Earth ages. And so we really want to know the comparison between the two. What's the difference between the two of those? So the difference, of course, is the time the person on Earth ages minus the time the person in the plane ages. That's what we're really interested in the answer to this question. So if we look at the difference between those two, our difference then, our answer, is equal to, well, the time 236,000 over 210 that the person on Earth ages minus the time 236,000 over 210 times the square root of 1 minus 210 squared over 3 times 10 to the 8th squared. That's the number that we're interested in. And we kept it all in its numbers because these are really, really tiny numbers. So when we plug that in, we find that the difference in time is 27.5 nanoseconds. So after that trip, the pilot is 27.5 nanoseconds. So that's 27.5 times 10 to the minus 9th seconds. Really tiny. Younger than his colleague on Earth. All right. So again, just kind of practicing using that time dilation, thinking about what's my proper time and what is the time that we're calculating in terms of the time dilation relationship, and then kind of familiarizing ourselves with it. Good job.